studio out there, sorry, the PhD out there. The tricky part about their site can get lots of minds. I've got a very short focal length, whereas they're trying to guide along the focal length, which is more technical to get right. Yeah, I'll pass out to Tony. Thank you, Tony.
Thanks, Robert. So the idea of this presentation is just to pass on what I've learned over the past year at Kumeu and over the past 5 or 6 years at home using PHD2. I've spent a lot of time optimizing the guiding. So this talk is about optimizing rather than actually getting it working in the first place. And there are plenty of YouTube videos on how to get it set up and working. So this is a complement to anything you can find. And I think there's some material in here that's pretty unique as well. Plus at the end, there's a few notes for Kumeu users, which could be of interest to you guys as well, because Kumeu is just a telescope. And I'm sure you guys have just a telescope. And they're pretty much the same. So PHD2 needs to see the stars. The way that it works is that it looks at a guide star and tracks that star and moves the mount so that it keeps on perfectly tracking that star. So the accuracy is going to be limited by how well it can see the star. So it's limited for a start by the seeing, by the conditions of the atmosphere. A disadvantage of it is it's reactive rather than proactive. So it waits until the star's moved off course before applying a correction. And so the problem with that is it's moved off course, so some of your photons already are on the wrong pixel in your camera, and then it puts it back on course. So it's not perfect. It can't create a perfect image. But for the technology we've got, it's the best that we can do. It gives an estimate of your guiding accuracy by the RMS figure. And if you know what that is, then an RMS of under 0.5 is probably as good as you're going to get with Auckland's seeing conditions. So you want to aim for under 0.5, but if your mount's not very good, then something between 0.5 and 1 is probably more realistic. But if you're not familiar with RMS, it comes into the discussion further on. At Kumeu, I've got an exceptional seeing condition, 0.19 arc seconds RMS, and that's the gold standard that I'm going to aim for at Kumeu, but it's extremely difficult to get it that good, but I've got a record of it just to prove it, and as the gold standard, I think. It's interesting, do you need to do guiding? And with modern CMOS cameras, you can take really short exposures, 1 or 2 seconds, and stack them all. And you can do that all night. And if you do that, you don't really need guiding. So there's a YouTube video by Richard Wright explaining that in more detail. So maybe you don't need guiding. But at Kumeu, we have to do guiding because we have to do 5-minute exposures. And over 5 minutes, you need guiding, even with our really good mount. So this doesn't cover setup. I'm assuming that you've already set up with it and that it's working and that you don't have any actual problems with guiding. If you do have problems, there's heaps of stuff on the internet on how to fix problems that you have, and there's user groups and all sorts of stuff like that. This doesn't cover that. The secret to good guiding is good focus and a circular pointy profiled star with a high signal to noise ratio. And the rest doesn't matter much, and it's not really worth spending too much time worrying about. It's not worth spending pages and pages of internet postings worried about, and it's probably not worth the rest of staying for the rest of this presentation, because if you can get a good, sharp, circular, pointy profiled star, you're 99% of the way there. So if you want to walk out, you can leave now. PHD is still short for push here dummy, and it's supposed to be usable by dummies. And so you don't really need all these extra tips and tricks, but I found them useful, and I I enjoyed working them out, and you know, you've got to do something to play with when it's cloudy. There are instructions. You set up PHD2 and you go to the help file and you get the basic quick instructions, and that's basically all you need. Expectations. For the altitude of the target that you're imaging, less than 25 degrees, expect poor guiding. 25 to 33, poor to barely acceptable. There are a lot of targets in Auckland that are around about 33, so you know you're on the limits of guiding there. Acceptable, 33 to 40, 40 to 50, good, and then greater than 50, and that's when you can raise your expectations. Greater than 50 and less than 0.5 RMS is probably what you should be aiming for. So don't spend too much time trying for perfection, especially if down low levels. So Kumeu, this is the best example I've got, and it's 0.19 RMS arc seconds, the average error, and it's a quarter of a pixel. So your fuzziness is a quarter of a pixel, and you have to live with that. There's not much you can do about that if you're using PHD2 with the kinds of mounts that we have. One thing to note here is that there are very few deck corrections. So the deck line is the red line, along here, and it's hard to see because all the lights are on. I think we should turn off the lights. And it's hard to see, but there are just 2 deck corrections. You only need deck corrections when you don't have very good polar alignment. And Kumeu has very good polar alignment. So that's an important point, because if you notice that if you've got good polar alignment and you've got a lot of deck corrections, then you've probably got too many corrections and you probably need to make your guiding a little bit less aggressive. So at Kumeu, look for the and if you have them, then you have them. First step for any guiding, most guidance are due to the mount. 3 main things: service the mount. Second thing is to optimize the balance. Balance reduces strain on the motor and makes the motor more responsive. And the third one is to optimize polar alignment. Now, some manufacturers say for balance the mount so that it's east heavy, and that keeps the gears meshed. And if that's the case for your mount, then it's probably best for you to do that. Just make the mount slightly, ever so slightly east heavy. And for some mounts that have a lot of backlash, they say deliberately polar misalign by 10 arc minutes, so that you don't have to keep on applying deck corrections in opposite directions. So those are specific commands, specific pieces of advice for specific mounts, and they may or may not apply to you. They don't apply to Kumeu. Service the mount is pretty important. The Astronomical Society has a ZEQ 25 mount that you can borrow and learn on, and that's the first mount I played with. And when I first used it and didn't do any guiding, I got these zigzag stars. And then Steve opened up the mount and serviced the motors and closed it up again, and those zigzags disappeared. So keeping your mount serviced and greased and all that stuff is probably a pretty important step. And it may even apply for a brand new mount that comes straight from wherever they come from. It may need opening up. It may need belts to be tightened and stuff like that. So the first step is to make sure the mount's serviced. The second step is to make sure the mount is balanced. Now, you might have heard of, over the last few weeks, of this AI thing that's on the internet, ChatGPT, and you can ask it questions and to talk to it, and it gives pretty intelligent answers. So I asked it, how do you balance an equatorial mount? And it gave a pretty intelligent answer. It reads good English. It's slightly wrong. It talks about using a spirit level. I don't think you need to use a spirit level. But it gave a pretty intelligent answer. So it can put together good English, though it's got no idea what it's talking about. So I just put that in as curiosity. Balance is a 6-dimensional problem. The thing is, balancing is getting the centre of gravity of whatever's moving exactly in the centre of the bearings. And that puts the least strain on the motor and it gives you the best guiding. Now, the centre of mass of the movable part of a mount can move in 3 dimensions. It can move left and right, up and down, in and out. So it's a 3-dimensional balancing problem, and there are 2 of them. So that means there are 6 dimensions. So a precise balancing can be a bit tricky. Now, I'll show it using my little model. This is balancing the deck. Needs more glue. Don't do that to your real scope. So you can move the deck axis till it's horizontal, and what most people do is they can move it left and right to get balance. But you also need to balance it up and down, and to do that you move it to right angles, and then you need to move it left and right. Most people don't do that, and you don't need to unless you've got some junk that's attached to it, like a finder that might stick out, or you might have a guide scope that sticks out a little bit, or a Newtonian will have a big eyepiece thing that sticks out. You need to move everything to be symmetrical. And then the 3rd dimension, in and out, you can't do that on the deck axis, because if you go out, it falls off and falls on the floor. So you can't do the 3rd dimension on the deck axis. Then you can do the RA axis, and what most people do is move it horizontally and then move the counterweights to balance it in this direction. But you also got the up and down direction, and if you balance the deck properly, then you won't have to move it in the up and down direction. And you won't have to move it in the in and out direction either. So if you've got a good equatorial mount with 2 axes, it's reasonably pretty easy to balance it. You just want to be careful and try as much as possible to get it really balanced. Where you run into trouble, that's the right ascension. I know it's step anyway. Where you get into trouble is when you get these star trackers. And you can see that this is grossly out of balance. This balance is 1 axis, and that might be okay. But you can see that the centre of gravity of this is way out here, and it's putting a lot of leverage on this bearing. So the first thing you want to do there is to move that camera back. And this is these are photos that you see quite a lot on these star tracker mounts. This is another example. I forgot to mention one thing. I'll mention it later. This is another example that I got from the internet, and that's grossly out of balance as well. That's grossly out of balance. This one is, and I showed you how to get it back into balance. So the centre of gravity is round about here. It needs to go back there. There isn't any way of doing it because they don't provide a slider. This guy has a guide camera, which is unbalancing it in the X direction. So this is unbalanced in the X direction and the Z direction, although it is balanced in the Y direction. So these things are a real pain to balance. And the cheap little mounts, so the motors aren't that good quality, and it really pays to really get the balance right. Probably the best way to balance these things is to point them where you want to image and then balance. And to have a good L bracket for your camera, and an L bracket lets you slide the camera along the bracket. This is pretty important because this may be the way that you start off imaging, and it's the way I started off. The other thing is, and all these mounts have the same problem, that the counterweight should be moved up as close to the axis as possible. And when you do that, you need more weight. But the formula for moment of inertia is an R squared formula, and so you really benefit from reducing R. So the fact is that, and it's very unintuitive, if you double the weight, you halve the strain on the motor. And that's unintuitive because everyone wants to use less weight. So they put the counterweight as far out as they can. No, put it as close in as you can, even if it means using more weight. So half the weight, double the weight equals half the load on the motor. And for these mounts, that will definitely improve your guiding. And that's a bad weight position, that's a bad weight position, that's a bad weight position. So for this, in summary, and this is an actual example of someone posted in the Facebook group for guiding. They said, why isn't my guiding very good? And there are two ways to fix it. Move the weight up and move the camera back. Polar alignment is important for long periods of guiding. The way that mounts work is, equatorial mounts and star trackers, is that the south celestial pole is up here and the tracking rate is a certain rate around the pole. But if you point your mount away from the pole and still have tracking so that it follows the guide star is going in a big arc like that. But the mount is still tracking, rotating like that. So it'll rotate. So the guide star will stay exactly in the center of the guiding image, but the whole frame will rotate about the guide star. So as far as you can, get good polar alignment. It will reduce the work that PHD2 has to do, and it'll avoid field rotation. How much will it avoid? Well, there's a calculate field rotation for a polar alignment error calculator on the internet, and you can Google that to find it. Probably don't need to do any calculations. Just make sure your polar alignment is as good as you can get it. It's really bad when you have an alto-azimuth mount, because instead of pointing there, that's pointing up there, which is a long way from the pole. And so field rotation kicks in pretty quickly when you have an alto-azimuth mount. And PHD can still guide with an alto-azimuth mount, but I haven't tested it, so I don't know how good it is. But even if the guide star stays dead centre, everything else will rotate around it.
It's only, I forgot about it doesn't know what the mount can't take that pulse signals from PHD.
Okay.
So you can't either.
What about an ST4 cable?
No, the mount itself cannot accept those signals.
Okay. Yeah.
I
So that's just a theoretical discussion. That's an extreme example of polar misalignment.
Yeah,
But it's,
other mounts that you can use PHD to guide for. There are a few people that have done it, but again, as you say, it's not always so good. Yeah.
it could be, if you've got one of those, a good idea, instead of having it point straight up, just roughly point it at the pole if you can, and that'll reduce the load on PHD2 and reduce the field rotation. But I haven't tested that. Everything I'm talking about tonight, I've made a point of testing myself, except for where I say I haven't tested it. So.
By the way, I've got a PHD25 and I've used the other one, which is the observatory one. The observatory one has jagged lines, like the one which you showed in the photo.
I tested that after Steve serviced it, and those lines disappeared. So I guess these mounts, some mounts might need a lot of servicing, especially if they spend a lot of time in people's car boots and things like that. So
Just I had it in June.
Yeah, I did it a few years ago though,
Yes.
so it's had a lot of use since then.
Yes.
It's a
And
good
I've got a ZDQ25, but the motor keeps flying.
Does it?
Yeah. Because of the overweight. 9 kg, my camera and telescope weigh 8.1 kg, and Steve told me to use 9 kg on a short mount, on a short bar, and what happens if the motor blew? So I got it longer, and the motor doesn't load with that.
Okay, so it's probably important not to overload the mount beyond its capacity as well.
Yes.
But I can't testify that because I haven't tested it.
Because the mount's supposed to be it's supposed to be 12.3, and 2/3 of the thing is roughly exactly around about the same as what 8.2, which is basically just about bang on its limits.
Yeah, it sounds very close. Around about half of what they specify is probably safe.
Neville's story is actually quite a good one because he did have problems with a couple of motors, and what we did work out is that it was a balancing problem. So the way that his OTA was set up, it couldn't be properly balanced, which puts extra load on the motors. Now the ZEQ being quite an old mount, the motor controller and the motor, particularly the current sense on the motor, wasn't very good. So over time, it increased the load on the motor and essentially burnt out one of the windings. So Neville's had a couple of motors. Unfortunately, we can't get the motors anymore. And Neville was also using a long bar and a smaller camera. So any unbalanced, any issues with the balancing, or obviously anything, if you have any collisions with the mount, or you knock the bar, a lot more load on the motor. So really important, the stuff that Tony's talking about if you want to look after your mount.
And it especially applies to us because we don't use expensive mounts. We tend not to, or we start off and we don't use them. So some tips: orient the guide camera so that north is at the top. It doesn't affect your guiding. Guiding will work in any orientation. But if you're wandering around the sky, it helps to know which way is up and which way is down, which way is north. Very important, focus the guide camera. And this makes the biggest difference at Kumeu. There's a big difference between focused. I suggest using sharp cap for focusing and using multi-star FWHM measurement, because it gives you a graph of how the focus is changing as you're fiddling. Whereas if you use the HFD in in PHD2, it doesn't give you a history, so it's a little bit harder. So you're trying to minimize this number 3.62. And you go in and out, and then, you think, do I need to go in or do I need to go out? Oh, no, I can't remember. Whereas with SharpCat, you've got the chart, and so you can see that, round about this region here, you're in a good spot, and then you can go back to it. So I suggest you use SharpCat for focusing. It's very difficult to focus a guide camera for lots of reasons, because you touch it and the mount just wobbles and things like that. So focusing tips: use long exposures, longer than what you'd use for guiding. So use 10 seconds, and that averages out the seeing. It's a myth, and you can see these myths on the internet. They say defocus your stars slightly, and that gives them a better shape, so PHD2 works better. That's not true. PHD2 works best with the tiniest stars. If you know what an off-axis guider is, OAG, then you've got to focus. You've got to focus the main camera and the guide camera at the same time, at the same position, and that can be tricky, and that can take a lot of work, and that's worth spending quite a few hours on to get right. And I've spent quite a few hours at Kumeu messing around with that, getting that right. If you're using filters and the filters aren't parfocal, then changing filter can actually change the focus on your guide camera. So some people have motorized their guide camera focus to get around that. I find that the focus at home, for me, doesn't make any appreciable difference, so I haven't had to do that. And at Kumeu, the filters are reasonably parfocal, and I haven't found any advantage in refocusing the guide camera every time I change a filter in the main camera. But your experience may differ. And at Kumeu, it pays to focus. For OAG, you're actually not looking at the main camera frame. You've got a separate frame off the main one. So you're looking at stars on the edge of your imaging circle, and that's where you have the least quality, and that's where your lack of collimation shows up the most, and where you can get funny shaped stars. So my experience at Kumeu is that if you've got funny shaped stars, focus to get the most circularity in your star. And remember to focus the main camera first before you start to focus the guide camera, because sometimes I've forgotten, and then you're just wasting your time. So that's advanced stuff if you have an off-axis guider. And most people don't start with an off-axis guider, they start with an off-axis telescope, so they're using 2 telescopes. If you have a focus motor, you can focus the main camera and then plug in the focuser for the guide camera and focus the guide camera and hope that they both focus in the same place. And if they don't, then you go backwards and forwards between the 2 cameras, adjusting the focus on the guide camera until they focus in the same place. And that can take a few hours, and I've done that. And so that's why I don't like people going along at Kumeu and adjusting the focus of the guide camera when I've spent several hours trying to focus it into perfection. So step 2, first step is getting the mount okay. Step 2 is ensuring that PHD2 is properly set up. There are 2 main things to set. There are the image scale in arc seconds per pixel, and here it's 0.48, and there's the RA guide speed. RA guide speed, not really sure, 100% sure what that is, but if you use the wizard in PHD2 to set up the camera and the mount, and you have the camera and the mount connected to PHD2, it can query the camera to find the pixel size of the camera, and it can query the mount to find the mount's guide speed. So you don't have to worry about these two things if you use PHD2's wizard to set up. And it's recommended to use the wizard. Some mounts, and that applies to my mount at home, it doesn't have a natural RA guide speed. So you can set it to any value between 0.5 and, in my case, 0.9. You can't set it to 1. I don't know why. So yeah, it's hard to find manufacturers' recommendations for the guide speed. Some manufacturers say use guide speed 1, and that seems to be the most common number. But my mount can only be 0.9 at most. And I have found that playing with 0.5 and 0.9 does work better than 0.5. So if your mount does have a choice, try the higher ones first, I suggest. But my experience with my cheap mount is that 1 works. At Kumeu, you use 0.5, and I don't know how to adjust it. I don't think it can be adjusted. Can it?
It's adjustable in the mount settings. I believe it's the percentage of sidereal speed, so 0.5 is half sidereal speed.
Something like that.
So it can be adjusted on the sky.
One thing they do say is some mounts want to use 0.1, and that's too low. So if your mount wants to use 0.1, see if you can adjust it. And in the end, I think it doesn't really matter, because you can adjust the aggressiveness of PHD2 to see how aggressive it changes the guide speed anyway. So I'm not sure that this is that important. So I wouldn't worry too much about it. Use the wizard and choose the value that the mount thinks it wants to use. So if the pixel scale isn't very good, recent versions of PHD2 will warn you. So here at Kumeu, if we use binning level 1 and our focal length of 3250, then it says the pixel scale of 0.18 arc seconds per pixel is too low. The PHD2 software authors recommend 0.5 arc seconds per pixel. So see how close to 0.5 you can get. And I think that's something to do with average values of seeing. I've tried at Kumeu different values, binning 1 and binning 2, and hasn't really made any noticeable difference. So maybe you don't need to worry about that, except that it's quite easy when doing the setup using the wizard. If it's low, if PHD2 complains, change the binning to 2, and it makes the pixels twice as large. Mount guide speed, PHD2 gets it from the mount. In this case, it's 0.5 at Kumeu. Just live with it. Your mount may or may not have ASCOM settings. Make sure that the ASCOM settings look reasonable. And at Kumeu, you need to make sure that use direct guide is ticked and can get pointing state is ticked. Your ASCOM mount settings will be different. Just eyeball them and see if they make sense. Advanced settings for PHD2. Use multiple stars, set auto restore calibration, set reverse deck output after meridian flip. If guiding doesn't work after the flip, then unset that. That's trial and error. Focal length, you know the focal length of your camera, of your telescope. And assume deck is orthogonal to RA at Kumeu. I think for most mounts, put in that assumption, and it lets PHD2 improve the calibration slightly, because it makes an assumption, so it does a least squares fit, assuming right angles, and comes up with a slightly more accurate answer. Not that important. As I've said, everything from the first 10 minutes of this presentation onwards isn't that important. So this is just an example of using the wizard. A couple of things you should do in the setup for PHD2 is set the minimum star HFD to 1.5 instead of 1, and that will avoid guiding on hot pixels, because hot pixels will have an HFD of 1, and if you make it 1.5, it'll say that hot pixels aren't big enough to count as a star. Otherwise, you'll end up with guiding on hot pixels, and your guiding looks pretty good. Looks spectacular, but it's not really guiding, it's just saying this hot pixel isn't moving. Set the minimum star SNR, signal to noise ratio, high to avoid guiding on dodgy stars, but not so high that you get star lost messages. So set it as high as you can without getting lost star messages. So that's a bit of trial and error. When in doubt, set it to 20 or set it to 10 or set it to 5 and don't worry about it. It's not that important. Use auto star selection. Let PHD2 choose its own guide star and it'll do the best job. Don't you try to choose one. Set initially exposure to auto and let PHD2 choose auto exposure. Click on the brain to get nice pointy stars. I should have made that clearer. Click on the brain and change the gain of your camera to make sure your stars are nice and pointy. You might have too much gain and your stars have a flat top because they're saturated. Or it might be pointy and it's not the maximum value your camera can provide, which could be 65535, and you might get 5,000 out of that. You might want to increase the gain so that your values are higher. So this is what you want, a nice pointy star, and the peak is 46713 out of 65535. So for this one, I could increase the gain a little bit more so that the peak of the pointy star is closer to 65535. Oh, I've flicked on to the next slide. That's a good pointy star. And then that's not, it's saturated. Well, it's not really, but that's what a saturated star looks like. It's not really because otherwise the peak would be 33852. But I didn't have an example of a flat top, properly saturated star, but that's what a saturated star looks like. And you can tell that it's not pointy, so it's going to be harder for PHD2 to guide on it because it's going to be harder for it to find the center of the star. So optimize the signal to noise ratio if you can. So change the gain settings and the exposure settings to optimize the signal to noise ratio if you can. It's not that, if you can't, it's not that important. Multi-star guiding, the lower the quality of the mount, the more that helps. Depends on the mount. Wide field of view benefits from multi-star guiding. So turn it on, it doesn't hurt. Now, this is the most important thing of the whole presentation. You've got everything set up, you've got all PHD2 settings set, and you've chosen your guide star or your guide stars. What do you do next? The next step is to point the scope where you want to image and run the guiding assistant. And this is so important that you should do it every night and every time you change the target. And if you're really fussy, do it every 2 hours during the night, because atmospheric fluctuations occur continually through the night and night to night. And the guiding assistant will choose for you the optimal settings for RA min move and DEC min move. And you just hit the apply and it'll do it automatically. And you don't even have to know what those things are. It'll point out the first time you do it. The other thing is that's of useful is the right ascension maximum drift rate. Because the faster your scope is drifting, the faster the guide star is drifting, the more often you need PHD2 to make corrections. So this is 0.18 pixels per second. So if you leave it for 5 seconds, PHD2 could have drifted off by a whole pixel. So 5-second exposure is too long for this particular setting. So in actual fact, PHD2 is suggesting an exposure of 1.3 seconds. And that makes sense, that it's about 1/5 of a pixel. So check this value and maybe manually set it to 1.3 seconds approximately. Instead of auto, set it to 1.3 seconds perhaps. But this, keep forgetting, the guiding assistant is the most important and useful thing you can do. So this is a good point now to leave this presentation, because you've learnt pretty much all that is, you've learnt 99% of what's useful. The guiding assistant shows what your mount is doing without any guiding. So you can see that the red line shows that there's a bit of drift. So your polar alignment isn't perfect. And we know the polar alignment error is 0.3 arc minutes. It's a bit strange because it drifts down and then it goes back up again. I'm not sure why it would do that. That's possibly atmospheric or something like that. Because you'd expect that if your polar alignment isn't perfect, your drift would just continually go in one direction. So, yeah, it gives you a rough idea of what's going on and isn't actually all that useful. This is your RA error, and you can see that it's periodic. And that's pretty normal with our mounts because the gears go round and round in circles and they're not the perfect shape. So the gears will make a bump and go around, then bump and then bump. And you've got probably more than one set of gears in there. So gears add periodic error. What's important here is to see how rapid that periodic error is. And here, it went to 4 arc minutes pretty quickly. So you need to make sure your guiding corrections come rapidly enough to correct for that amount of movement. I don't know what the time frame is. I think it's over a few seconds. So you know that the periodic error is so many arc seconds per second, and so you need to adjust your exposure so that you can correct that error quickly enough. So it's worth spending a lot of time studying how this thing works and practicing with it. Backlash, there's a backlash setting. It's in the bottom left corner here. It's not, you can't see it. It can measure the backlash and the declination of your mount, and that can be useful to know. Kumeu has no backlash, and I think that's because it has software backlash compensation. But you always get backlash when your gears reverse, because it takes a few, you're going this way, and then you have to stop and go back, and all the gears have to remesh. So the bottom one goes back a bit before the top ones start remeshing. So that's backlash. And it helps PHD to know what the backlash, how much it is, and it puts in the compensation for it. And there's the compensation apply button there. You only need to check the backlash very infrequently. You don't need to check that every night, and you don't need to check it every hour. Just check it every couple of months. And PHD2 will remember the settings. So this measure backlash, when you do the guiding system, generally you want that unticked. And usually you forget to untick it. But I'm starting to get better at remembering that now. A guiding system for every target and every night and every altitude is your friend. So now we get to the tricky stuff. This step 5 is to tweak the PHD2 settings. And they're a lot simpler than you think. The default settings work, and the guiding assistant changes to the default work. So you don't need to worry too much about them. But just know that this total error, RMS 0.19 arc seconds, that is the standard deviation of these deviations from 0. So the smaller that number, the better your guiding. Well, the better the tracking of the star, not necessarily the better of the guiding. And you don't need to worry too much about them, except that you should record them from night to night so that you get into the habit of being able to judge how good the seeing is on any given night. So you become experienced. You become an experienced astrophotographer, and you say, oh, you're looking at the twinkling of the stars and say, oh, tonight's a good night. And then you see that this value is low, and you say, oh, yep, it's a good night, all right. And when you come to analyse the images and picking your best images, it helps for picking the best night's images if you're imaging over several nights. So that's a pretty important number to record. And I can say now that the best guiding I've seen at Kumeu is 0.19 arc seconds, RMS, and that's a target if you ever go out there to do your own imaging, which you're quite welcome to do. 0.19, it'll be difficult for you to achieve that or beat that, but it's the gold standard, useful to know. This other number, RA-OSC, measures how frequently the right ascension, which is the blue, oscillates above and below 0. You want that to be about 0.5, so that it spends equal time on either side and is just randomly switching sides. If it's too high, that means you're aggressively switching sides, and you're switching sides too much, too often, and that's a bad thing. Now, guiding has smoothness in it. The hysteresis applies smoothness, and that reduces that frequency. And so a value of less than 0.5 is okay as well. So that's what the hysteresis is. It smooths things out, just like a moving average smooths out time series. If you're used to using moving averages to watch time series, that's what.
Can you use the hysteresis then to adjust your RA oscillation? Is that what
you can, but I suggest leaving it at 0.1 and never touching it. It shouldn't really be there. There's no need for it, because you can adjust the oscillation by adjusting the aggressiveness. And RA aggressiveness, so don't change the hysteresis. Leave it at 10. RA, and don't manually change min move and min move. Let the guiding assistant set those values. The min move is if the star doesn't move less than, if the star moves less than that amount, then the mount's not going to do anything. PHD2 isn't going to do anything. So the star can wobble and the mount will just let it wobble and not apply any corrections. So if you've got very good polar alignment, then you shouldn't be adjusting, you shouldn't be moving the declination at all, just the occasional tweak. And so min move should be reasonably high for that. But the guiding assistant will set that for you. The two things that you can set are the aggressiveness. So what PHD2 does, it looks at the star, it looks how far off course it is and says, oh, I need to apply this much correction. But the aggressiveness says, okay, let's not apply all that correction, let's apply 90% of it or 50% of it. So it reduces the correction that it's going to apply. So if you have aggressiveness at 50, that's 50%, then you're telling PHD2 to spread that correction over 2 moves. And it's best not to be too aggressive, otherwise the mount goes jerking all over the place. And it's better to be under aggressive, because if it doesn't apply enough aggressive the first time, it'll apply some more the next time and more the next time. So it just adds a bit of lag to your guiding. Yeah, it's hard to find values, good values for those, which means that the values you use, well, PHD2's defaults are pretty good, and you probably don't need to adjust them. But it's useful to know what they do, and you may need them if your mount is too aggressive. So that explains that. But anyway, the lesson is use the guiding assistant. So a tip is, for round stars, you want the right ascension and declination moves to be roughly equal, the RMS to be roughly equal. And so if your deck guiding is better than your RA guiding, you may want to make the deck guiding a little bit worse than necessary, so that your stars become circular again. So yeah, you may want to adjust the min move or adjust to lower than what your guiding assistant suggests so that it's more active than it needs to be, or you may want to make it more aggressive. And so that's just a classic example of 2 wrongs making a right. Reducing your declination guiding performance to match the RA. Generally, RA is worse than DEC for the kinds of mounts we use. But remember, that's not the only reason that causes eccentric stars. There are other reasons, such as wrong polar misalignment, back focus spacing wrong, spherical aberration, flexure, and stuff like that. So these are tips and tricks, and there's a lot of them. Don't use ST4 guiding cables, because you have to recalibrate the camera guiding every time. Set the mount to king rate if you've got king rate rather than sidereal rate, because king rate takes into account atmospheric refraction, and so it adjusts the speed of the mount depending on where it's pointing in the sky. Try predictive PEC, because that's the only algorithm that tries to predict mount error, and so it may produce better guiding for you. It didn't work for me. You only need to do the guide camera calibration once, and as long as you don't touch the camera again, that should stay in place for months. And Grant says that upstairs he only adjusts the guide camera calibration once every 6 months. Do your calibration near the meridian, celestial meridian, which is over there, and near the zenith. A trick to get there is in the drifter line tool of PHD2, enter 0 for meridian offset and declination, then hit the slew button, and it'll put the mount in the right place. Or, if this is your scope and it's pointed at the celestial pole, then at right angles to this, it's pointing at the celestial equator, if you're doing it manually. So make 90 degrees. Make sure the calibration moves. It may not. If you want to, you can review the calibration, make sure the 2 axes are perpendicular to each other. This is a calibration that happens that if you do it at Kumeu and you forget to set one of the ASCOM settings, those aren't perpendicular, so not a good calibration. If you're going to buy a guide camera, buy one with a big sensor. And this is just a table to convert between inches, which is the size they measure sensors in, but it's not an inch. 1/3 isn't 1/3 of an inch. Monochrome cameras have twice the sensitivity of color cameras. Use a camera with more than 8 bits, so you get 16 bits. That gives you better SNR. Don't worry about that. Don't worry about that formula. I've verified the formula. It seems to be pretty good. Record your guiding assistant values every night, and record your seeing, and record your SNR values. I've explained that before. Save your PHD2 log files, because you may want to review them. There's a log file viewer. There's a Pen Pro log viewer. Fiddle with your mount clutch settings, like the Star Adventurer. Apparently changing the collar so it's not so tight produces better tracking. For my mount, apparently loosening the knob produces better tracking. So play with that. For mounts with encoders, if you've got lots of money, use the low pass 2. They say don't chase the seeing, which means don't use low exposure values, but try it, because I find low exposure values, less than half a second, work quite well with my mount. You may need to, if you lose stars a lot, you may need to change the search region. Nudge the mount north before you do a calibration, and that meshes the gears properly so they're all ready for the calibration. If you lose stars due to cloud, just remember PHD2 may not find the star again. If you've ever changed the settings, it can take a long time to see if your change has had an effect, because there's a lot of randomness in guiding. When using a color camera, for the main camera, always use dithering, because stacking won't remove debayering artifacts if the stars don't move. That's got nothing to do with guiding, but I thought I'd have plenty of time by now, but I don't. You can simulate using your without setting up your telescope. You can do it in the daytime by using simulations and your ASCOM settings. There are lots of myths on the World Wide Web, so read official stuff like the PHD2 user guide and analysing PHD2 guide logs. There's Bruce Waddington runs the group. He's the author of PHD2, so he knows his stuff. If he says something, then it's likely true. Find his videos. There's 2 good videos by him on YouTube. This is his wisdom. It's pretty good. It's a pity you're only getting half a second on this slide, but the slides will be available, and this video is on YouTube. And I'll go over the Kumeu stuff separately with the Kumeu people. These are the Kumeu settings. And that's actually what the guide camera field of view looks like at Kumeu. So the big one is the main camera. It's not aligned properly north-south. It used to be. And I saw Steve do it. And the guide camera isn't aligned north and south, and it's not aligned with the main camera. And that's my fault. I aligned it with the main camera, but then I twiddled something and forgot to realign it. So, this is a picture of what goes on at Kumeu. And this is, if you're using an off-axis guider, this is a good mental picture of what's actually going on. Now we can go into the planetarium, can we?
No, because the operator's sick, so we're going to do the sky review in here.
Okay.
Very good.